My name is K.Vandiver. I'm a professor in the Ocean Engineering Department and chairman of the MIT faculty for a few more days anyway. I'm standing in for Louis Cabot as the moderator of this afternoon's Technology Day panel on ocean recreation and sports. There we go. Did you all hear that, I hope? Testing? Okay, we're back on it. I won't repeat it all. My name's K.Vandiver. I'll be the moderator this afternoon. Our four guests are Professor J.Milgram from the Ocean Engineering Department, T.Van Deusen, who owns his own company and is going to talk to you about his exploits, among other things, in making racing shells. D.Liu from American Bureau of Shipping, and P.Quigley, who I saw in the Building 7 lobby a mast and sail from a sailboard with carbon fiber components from Fiberspar, Peter's company. All five of us are graduates of one degree or another of the Ocean Engineering Department, and I'm not one of these people who gives lengthy introductions, and since I know roughly what each of the speakers are going to talk about today, I think I'm going to let them speak for themselves as to the kind of things that they do and are interested in. We're going to follow what the order in the program, which is Professor Milgram and then Peter, Ted, and Don following. The format that I'd like to use this afternoon is each one has a presentation of 15 minutes or so that they would make. And if you have I'll entertain a couple of questions after each presentation if you have something specific you'd really like to address to them right then. And at the end of the fourth presentation, the last presentation, we'll open it up to a more general audience participation discussion, and you can ask questions of any of the speakers. So with that, Jerry, I'd like to start, please.
Well, from this morning's session, you can tell that what we did at America Cubed was a different approach to making fast sailboats. So that's a kind of ocean engineering which I'm going to describe here, this different approach. And Kim's volunteered to put on the view graphs for me, so we'll just start. What I show you here is a flow chart of how one traditionally designs a sailing boat in this day and age. There is very little science in it. There's some experience, and if you start with a fast design, and you need to change to a new design and can modify your fast design, you got a chance at doing something that's fast. Maybe. You've all seen the difficulties of this approach. Some designer will come out with a bunch of fast boats, and 4 years later he'll be an also-ran. And that's because he's stuck with this. He can't expand. So this is how it's normally done. And we didn't do that. Kim, you're gonna have to pretty much stay pretty quick. We're going to go through them pretty quick. That we concluded at America Cubed that was not a good approach, because what I show you here as a function of wind speed is the difference in time it takes to sail around the course, both for the windward legs and for the entire course, when you change the resistance of the boat by 1%. And so it's a huge effect. So in 10 knots of breeze, if you've got 1% more resistance, you've lost the race by 33 seconds. So you've got to do better than messing around, which is what the traditional yacht designer does. The late Van Clark used to call those people goddamn boat drawers. And those of you who know Van will appreciate the comment, or who knew him. The approach we took at America Cubed, I've got on the next view graph. And this is the flow chart of what we did. And the items that have orange inside the boxes are ones where there's lots of science. And there's two big design tasks, or three design tasks. And the flow goes both ways to those because the science has to feed back to the designs in order to come up with something that's very fast. You'll see at the centerpiece of this technical approach are our velocity prediction programs. They're the key because they allow us, before you build a boat, to evaluate how fast they're going to be. And just very briefly going through this, you'll see you have to do some, you might call this preliminary design if any of you are big ship naval architects. Then you know something about the weight, you can design some hulls, you tank test them. You've got to somehow get sail forces, you've got to somehow design good sails, you've got to include the added resistance due to sea waves, and eventually you get down to design selection, some testing. There's some feedback loops here that aren't shown, and eventually you get to what you want if you do it right. Okay, can we have the next one? This velocity prediction program, which is the, just lost something, which is the centerpiece of the thing, can be viewed as a computer-based balance between hydrodynamic forces and aerodynamic forces. And the computer will change the variables that affect the performance of the boat, or that measure the performance of the boat, the speed, the heel angle, and the leeway angle, until these come into balance. And that's where you're sailing. So this isn't for dynamics, this is for steady state sailing. And it's simply a computer program, and the actual computational part's pretty simple. The hard part are how you model the various forces that have to go into the model. The next view graph's a block diagram of one of these velocity prediction programs, which is there to emphasize what a small part of the whole thing, the actual solving of the equations of motion are. The hard part are making the models. Making these models which determine the forces that affect the speed. And we're trying to get to a point where we can use technology for evaluating potential designs with resistance differences of something less than 1%. This is a bigger version of one of the view graphs Bill Koch showed this morning. What we did in our work is we decomposed the resistance of the hull into various components. Now, I need to explain to you that if you could test full-size boats, you wouldn't need to do this. If you had a full-size boat, you tested it has a certain resistance. But you can't test full-size boats. You can test models, or you can make approximation to portions of the resistance computationally. Each of them scale differently, or each of them has a different kind of error. And as a result, the decomposition into these various components is useful. This is the skin friction of the hull. This is the wave-making resistance of the hull, the skin friction on the appendages, the drag due to the fact that the boat heels and makes a side force to balance the side force of the sails, and the resistance due to the sea waves. Now, how big are each of those components? The next two view graphs will show you them. For sailing to windward, what I show here is the fraction of the total resistance that each of these components makes up. Now, Kim, if you could put on the next one and then do an overlay of the two. There's two missing here. There's the two that are missing, the resistance due to heel and side force and the added resistance. Now, if we can do an overlay and let him struggle with it. There we are. You'll notice that at typical windward sailing speeds for these boats, 9.5 knots or so, all the components except skin friction have the same order of magnitude, and skin friction is bigger. And they're all these are around 15% or so, and this is around 40%. And I ask you to bear that in mind, that each component of resistance is, in the conditions you care about the most, are about 15% of the total resistance. And the job that one has to do for potential designs is to evaluate each of those components and see how it affects speed. What the VPP does for you is it will tell you the speed if you know how big each one of these components and the sail forces are. There's been a lot of work done on computational hydrodynamics for residuary resistance. And the people who do it pride themselves on how good they are. They say, look, I got it right within 10%. Well, 15% of 10%, 15% of the resistance, 10% error is 1.5%. It's a minute around the course. Forget it. It's not good enough. Those people are focused on their computations and not on the job of winning a boat race. And that's got to be realized, and we realized that, and we realized we had to go to the towing tank. I've got 3 quick slides, if we can see them. If we can shut that off here, and if we're lucky, maybe we have 3 quick slides. Does this work? Well, I guess we're not going to see them.
Slide projector?
Where's the man? We got him up. There are no slides. Okay. Here you go. We have them in view graph. They're just not as good on view graph. Forget the slides. They go in. Here we go. I'd like you to show that one first. Well, you have to fuss around that one second, and that one third. That's third. There we are. That's a view graph of what goes on at a towing tank. And there's a couple things to see here that are important technologically. By the way, I think this guy's in the audience here. The models are big. Scale error in tank testing is a big problem. If you don't make big models, typically bigger than 20 feet or so, you're not going to get the resistance measured to less than 1%, to accuracies of at least 1%. The models have to be big. All of you, some of you are interested in sailboats, and you all know about tank fiascos. The business is loaded with stories of them. You'll see there are a lot of models. We tested about 40 models. We did 99 sets of tank tests. Each test was 105 runs. Those 105 runs count back and forth in the tank for 99 sets of tests, because we did retests in different appendages, was 1,500 miles in the tank, which is about as far as all our big full-scale boats sailed. So we went about as far in real distance at model scale as we did full scale. This shows you some of the instrumentation on the deck of the model. You have to do this tank testing right. There's a whole bunch of load cells in here and what have you. This is a heeled model, so you can see it. It's a very intensive process. And it's a process where if you want to play this game, it behooves you to do it right. Now I have a picture of a boat coming down the tank. Is that upside down? Yeah, here we go. There's the boat coming down the tank in the towing tank. And if you do that right, you can get the residuary resistance right, and you can get the best estimate of frictional resistances that you're going to get. It's not perfect, but it's as good as you're going to do. What about the other components of resistance? I mentioned before resistance due to appendages. And that's one thing where computational hydrodynamics can help you a lot. Here's a view of a keel fin and a bulb. These boats are bulb keelers. And these aspects of that fin and bulb are things that you can evaluate with computational fluid mechanics and look at their results in your velocity prediction program to evaluate how fast your boat's going to go. The next view graph gives an example of fiddling with the taper ratio, the width of the keel fin at the top to the width at the bottom. And you find that this is a measure of drag. It's kind of long versus taper ratio. And you can see that you can gain about 1.5% in keel fin drag. About 1%, say 2%, 15% of 2%, 1/7 of a percent, about 8 seconds. So if you change the taper ratio from this much to this much, this is the keel fin that's almost straight up and down, and this one's much smaller at the bottom than at the top. If you do that, you can gain 8 seconds. Well, that doesn't sound like much, but if you work at these things for a couple of years and gain that 8 seconds 10 times, you're a winner. So that you can do computationally. But computation won't do the whole job for appendages. You've got to do wind tunnel testing. And I show you a picture of an inferior wind tunnel test. That's upside down because the way that most of the wind tunnel tests are done is you mount the body in the floor of the wind tunnel. Here's the keel fin, here's the bulb, here's some winglets, here's some apparatus to measure the flow. Why do I say that's inferior? This was done by the Partnership for America's Cup Technologies, who's got some scientists that didn't come to MIT working for them. And they did these tests. Now, on the next view graph, I have just a sketch of how you do it right. And I'll explain to you why there's a difference. Turn it over. This model has a hull on the wind tunnel floor, and it has a rudder. And the reason that you need this is the flow up here is influenced by the curvature of the hull. And you're going to get the winglet angle wrong for sure if you don't put the hull there. Guaranteed. In fact, we experimented. We know you do. Also, when you change the lift on the keel fin, the trailing vorticity affects the rudder. So you've got to do it all. You've got to put the important stuff in. Now, this doesn't have everything. This doesn't have waves because wind tunnels don't have waves. So that isn't there. But within the restrictions that you have, you've got to do everything you can to get as far as you can. So what I've given you now is a brief vignette of how we get the various hull forces that go into the velocity prediction program. What about the other half? What about the sail forces? And this is a view graph of our measured speed made good to windward that we actually measured with one of our boats. And the dotted line was, when we did this, the predicted speed. And that turns out not to be good enough. In other words, you cannot evaluate one design from another if you have these kinds of errors in your speed predictions. In particular, the prediction completely fails to capture the phenomenon of when the wind gets below a certain level, the speed suddenly drops. We call that falling off the cliff. And depending on the design of your boat, you can move this around. You can move this down here, but then this is going to drop down. You've got to do some trade-offs. So we looked into why we had those problems. And what we did is we built the Sailing Dynamometer, or we refurbished one that we had, and this you saw from Bill this morning, in order to get the sail forces better. Can we take a look at this? That's a photograph of this Sailing Dynamometer. It looks like a sailboat on the outside, but inside it's really very different. And it has this frame. You can skip the next view graph, the one you had on, because everybody's seen it this morning, and we'll go to the one after that. It's built with an internal frame where all the sail forces are resolved. That's the one. Everything that's red here is hooked to the rig. Everything that's black is hooked to the boat, including the people inside. And that means that if a person touches something red, this thing's going to get the wrong readings, because the load cells that connect the red stuff to the hull are computer interfaced within the boat. You can measure forces on sails, and you can develop a mathematical model for sail forces with a device like this, which was a scale model of an America's Cup rig, sailed in waves. And we tried to find the best approximation we could to scaled waves, so we sailed in somewhat protected waters. And we developed a sail model for our velocity prediction program. And what I have next is the comparison between measurement and prediction after we got the sail model right. Okay? Now we had a way where if we tank tested a boat and if we designed some sails, we had a way of evaluating how fast it was going to go. And with that, one could progress towards design. And remember early on I indicated that there's feedback between the science and the design process. And the next view graph is more or less as a flow chart showing the kind of design process that we did. Now, once we got to the point where we knew we could predict speed if we had tank tests, we designed a group of models with systematic parametric variations, no shots in the dark. Each one was a systematic variation from the next one. We tested it. We analyzed its data. We learned the best parameters for San Diego. About that time was the World Championship racing before the America's Cup. We learned a lot because the technology couldn't tell us all, particularly about some aspects of the added resistance due to sea waves. And one of our designers, we had a 10-person design team, and one of the designers was very good at recognizing the boats that did best in waves and why. And that was very important. That got dialed in. We designed a second set of models, tank tested those, analyzed the results, and figured out what is it that makes fast boats. You see, this was the feedback. And that allowed us to design our final boats. And they were very fast. Finally, last view graph. If you'll remember this morning, Bill Koch told you that just before the America Cube sailed in the America's Cup, we changed appendages. And we knew the appendages that we had were not optimum. However, we learned enough with our velocity prediction programs to use them to predict speeds for appendages that we never tested. And we knew we needed better performance in light wind, and we could sacrifice some performance in heavy wind. So we designed these new appendages, we built them, and changed the appendages before the America's Cup with complete confidence that these new appendages were going to work. And they did. And they did exactly what our predictions were. What you saw this morning from Bill's talk was the actual measurements of speed differentials, and these were the predictions. We predicted that with the new appendages, In a 7-knot breeze, we'd gain about a minute around the course. In an 18-knot breeze, we'd lose 1/10 of a minute. And that was very, very close to what we actually observed. So we were able, by using good engineering skills and some decent computer programming, to develop predictive tools that could be effective in the real-world situation. We'll leave it at that and listen to the next guy.
We can entertain a question or two now, and then remember later on we'll have a more open format after everyone's finished.
Hypothetically modifying what might be a laminar boundary layer film there, or obviously you made a couple of things with Teflon, but if you warm the hull or you put warm water at the bow, you can stream along, or put something ecologically acceptable, like a little salt water out there, or a little something to change the boundary layer, or whatever you call it. Would you decrease hull resistance?
Absolutely. The problem is you can't do it.
I don't mean for our contest, but strict rules.
No, I understand. Well, in our case, with rules, we were not permitted to use certain additives. We looked into potential uses of shapes that would encourage laminar flow, and this was one of our studies. I mean, I didn't have time to tell you everything. And we found that it would be rather ineffective in seawater because microscopic bubbles and particulates were enough triggers for turbulence that if you were operating above the critical Reynolds number, no matter what you did, it was going to become turbulent. You could make it laminar in your test tank that didn't have the particulates, but you couldn't at sea. And for that reason, we did not go to laminar flow sections. Sure, yes. If you, as you said, if you could heat the boat, I mean, but that would do something. I don't think that would be permitted under this rule, but perhaps under some other.
Back there. Two-part question. I understand the defense of the cup will be in '95. Where is it going to be, and do you think there are going to be major changes to the boat?
It's going to be in San Diego, and the changes will be incremental because enough of what our boats looked like has now gotten around. Plus 3 of our designers jumped ship and went to work for the foreigners, and but they all came from the West Coast, and so between what they know very well and what other people could tell by looking, I think there will be only incremental changes.
And the sail proprietary, or is that something that's being marketed?
Oh, the sail fabric? We'll have to talk about that later. I think there's probably some people in the audience who know that better than I do.
Jerry, are the two existing boats, will they be competitive in '95 in your opinion?
Well, one of them could be. One of the boats, Kansas is a very big boat. It was built in case the wind was much stronger than anticipated. But American Cube would be either competitive or very close to competitive. I can design a much faster boat right now. Whether the other guys are likely to come up with something that's faster too. So I would say competitive, but not a winner.
One last question, the lady out here.
I was just curious. You said some of you designed jump ship to the foreigners. I thought the design had to be by a national
Or a resident who's been in the country for a minimum time of 2 years prior to the start of the first race.
Okay.
That was May the 4th.
May the 4th, all right. I think we'll move on to our next speaker, P.Quigley, and we'll follow the same format, a couple of questions after he finishes, but there'll be plenty of time at the end for lots more questions.
Can I borrow your microphone?
I think we're good.
I think I'll just stand out there and use the microphones.
Okay, good. There is a pointer if you want it.
People will
have to bear with me a bit. I'm coming down with a bit of a cold, so if I doze off in the middle of my talk, you'll definitely have a reason to doze off yourself. So, what I'd like to describe, I graduated with a bachelor's degree from the Ocean Engineering Department in 1985. I was the recipient of a very wonderful academic prize called the Robert Bruce Wallace Prize that I received in '85 that paid for a full year of graduate study here at the Institute. So I think the one distinction that I bring to this panel is I think I'm the only dropout from MIT on the panel, because the 1 year of graduate study that I undertook here at MIT really was what really fostered the launch of a company which initially had to start in a very narrow application of windsurfing, which many of you have seen if you spend time on the water or near the water. All of us have seen windsurfers. But what was interesting from my perspective is that there was an emerging type of material which I felt had much broader application, and I began to become exposed to those materials while an undergraduate and a graduate student here. So what I'm going to do is describe a recreational sporting goods application that's marine-based, but I'm also going to reflect a little bit on the potential bridge from that sporting goods application to other applications in both industrial and commercial markets. And in many ways, a lot of the technology associated with the America's Cup ultimately can find its way into more diverse applications than simply winning a boat race. So I'm going to reflect a little bit on a very narrow application of windsurfing, but also reflect on how that might be applied in a broader sense to emerging industrial and commercial applications. So I'm going to start really just with a bit of background about what actually I became interested in. And I'm not going to read through this here, but what I want to describe is a type of material which many of you have been exposed to, but others really are still somewhat not exposed to. And the general class of material is referred to a composite material. And what a composite is, we're sitting in a room that's steel reinforced concrete, where you have very brittle and weak steel, concrete reinforced by steel members, which are very high strength. Composites have been around a long time. Reinforced straw brick is an example where the brick was very brittle. Going back to prehistoric times, people found if you added straw to the brick, you made a structural element which had a great deal higher mechanical properties. So what a composite material is, there's been a lot of innovation. All of us have been exposed to fiberglass really for 40 or 50 years in terms of recreational boats. Fiberglass is the dominant material these days in both motorboats and recreational sailing boats. And that's a form of composite material, glass fiber reinforcing a polymer material. Well, where are these materials being used? Because each of us in this room, probably whether we recognize it or not, has probably been exposed to composite materials. Where these materials are most used is in the aerospace industry. Applications, the B-2 stealth bomber that has all kinds of complex radar evading capabilities and has extreme lightweight. The next area where people have seen these the most is in sporting goods, and there isn't anyone in this room who's played tennis in the last 5 years that can find a tennis racket that's not made out of composite materials. I don't know, Jerry, what was the structural weight in America's Cup in terms of how much of the structural weight was composite material? Okay, so there's another good example. The America's Cup boats, in fact, the sails, the spars, the hulls, some of the appendages were made of composite materials. Golfers in the audience know that graphite and carbon fiber is becoming much more prevalent in the use of golf shafts as well as the heads of the clubs as well. So in the first two applications, that makes up about 95% of where composite materials are used, but they're beginning to show up more and more in other applications. People that wrap on the fender of a car will notice it doesn't quite sound like metal anymore. Many applications in cars are using plastics or reinforced plastics. So just to kind of reference what I perceived as an opportunity, really going back 10 years now, was if you look at this bottom pie chart, it's probably difficult to see in the back of the room. The chart on the left projects what the potential growth of the use of these materials are from a congressional office study back in 1989. And if you're thinking about starting an enterprise, it's always nice to see a potential growth curve that's one of these. It's not quite biotechnology, but it has the potential to be an industry which offers relatively rapid growth. If you look at that top section, is it focused in the back, or is it kind of, let's see what we can do here. There we go. If you look at that top pie chart, 80% of the circle is made up of aerospace, and about 15% is made up of sporting goods. What those two industries have in common is price is no object. If you're a golfer, if you can hit the ball 10 yards further and it's going to stay within the short grass, really the price that you're going to pay is really not conditional on does it cost $50 more for a set of clubs. I won't even refer to the costs involved with the America's Cup because all of us have read the stories and heard about it. I think in the sporting goods world, it's the closest thing that we could ever come to in the $700 hammer category, and that technology was heavily applied with the ultimate objective of winning a sailboat race. So there's another example that price wasn't really an object if you can make the sailboat go faster. But my contention was, and really an observation, was that these materials had the potential to be used in broader applications than just sporting goods and aerospace. So where does that lead us? As a graduate student, 23 years old, I decided that where an opportunity lay was in windsurfing. And another thing which I found relatively unique about my own experience is I think I'm the only one who ever attended MIT for the following two reasons. First was it had a sailing team, and this is in order of priority. Second, I could study naval architecture, and at age 14, I decided that the design of boats, if what I really was a professional sailor at age 14, the design of boats was probably the next best thing. So really, when I was a student at MIT, that's really what my focus was. I sailed on the intercollegiate team. I did an Olympic campaign in 1984 in the Finn class, and really that's what really made me tick. I was highly focused on sailing. To refer windsurfing to sailing in many ways is like referring skiing to snowboarding. They're almost two different sports entirely. The people that sail oftentimes don't have anything to do with windsurfing. It's sort of like windsurfing is kids, and people that sail sit down when they sail, and they have cocktails, and they go on the New York Yacht Club cruise and those kind of things. Windsurfing is really rock music and kids, and it's high energy, and it's jumping and sailing 40 and 50 miles an hour. But what the opportunity was for the use of a composite material in a windsurfer. And this is a section of a windsurfer mast. I'll just pass it around the audience to give people a feel. The thing that's most noticeable about it is that it's extremely light. It's about half of the weight of aluminum, and it's significantly stronger. And that's why in a case like the America's Cup boats, where there was really a high premium on reducing weight to improve performance, there was a willingness for people to use alternative materials. So I'll circulate this. Our company this year will produce more than 1 million linear feet of this tubing. And what that has led us to be able to develop is some very innovative manufacturing technologies which have the potential to use these types of structural materials in other applications. So I'm going to interrupt this discussion with a 5-minute infomercial here to give you an idea exactly of how this very lightweight and high-strength material is actually used in a windsurfing application. So Ralph, we'll start with you. We can pass that around. So what I'm going to put on here is this is a video that is kind of really a balance between a marketing video, but also it really illustrates the technology involved with combining fibers of different types with a polymer or plastic material. And the resulting material results very improved properties when compared to conventional materials such as aluminum. So I don't know if we need to turn the lights down, but let's give this a try.
Fiber spar masts. The lightest, strongest, and most durable carbon fiber windsurfing masts in the world. No other mast available today demonstrates the same strength at such light weight. In comparison tests designed to measure how far a mast can bend before it breaks, the competition's masts don't measure up. In test after test, fiber spar masts consistently demonstrate the ability to bend twice as far as their competitors. P.Quigley began working with composite materials at MIT in 1980 and developed the patented laminate that gives fiber spar the unique properties of lightness, strength, and bendability.
What the bend translates directly into is durability and strength. If you can bend further than the next guy, you've got a stronger product. That's the bottom line. Those masts weigh 3.5 pounds.
It's the combination of incredible strength and low weight that defines the fiber spar difference. Nevin Sayer, professional World Cup racer and 3-time national champion, has been using fiber spar masts and booms since 1986 and has been instrumental in their development.
Well, on professional ranks, everyone is so good that the equipment often is making the difference. And most of the guys who are sponsored by different sponsors, they have different boards, different sails, etc. The one thing that is fairly constant is the fact that we all use masts made by fiber spar.
Blatant commercial plug.
The rigs are lighter, they're more durable, they're easier to control. People can do things on a windsurfer that they never could before. It's taken the sport into a whole new realm.
Now, that mast can't break. Literally, it can't break when he does that.
The fiber spar difference begins with a unique and highly specialized manufacturing process. Carbon fibers are interlaced with 2 different fiberglass yarns to create a seamless, triaxial structure. The masts are constructed to be light at the top with a lower center of gravity for easier handling. The entire profile is narrowed to smooth the flow of air for superior aerodynamics. Fiber spar's specialized manufacturing process means superior reflex response. Your mast recovers quicker after a gust or pump for instant acceleration and increased speed. In fact, fiber spar carbon masts recover 4 times faster than fiberglass and twice as fast as aluminum. Most importantly, fiber spar masts are engineered to withstand just about anything.
You can treat the equipment in a way that allows you, while you're on the water, to be as aggressive and go for it as much as you possibly can, and the equipment is not going to be the weak part. It may be your body.
As important as the equipment is for professionals, beginners need it too. They need the lightest mast, the most durable mast, and the mast that's easiest to use.
At Rhonda Smith's Windsurfing Center at the Gorge in Hood River, Oregon, fiber spar's lighter masts make windsurfing easier and more enjoyable to learn.
Just recently, I had a woman in one of my clinics who could not get her sail out of the water. I went over to help her. I tried to get her sail out of the water. I couldn't. I turned to her and said, "You've got to get a fiber spar mast." The water starters are benefiting the most. I mean, they can now just lift the sail up effortlessly. It's not a bench pressed anymore.
Fiberspar has developed a series of tests to measure the critical performance characteristics of their masts to be sure that specifications for quality and consistency are met. Fatigue tests ensure that the mast will maintain its designed curve, stiffness, and reflex response over years of demanding use. Other tests measure the forces that a mast can withstand. And of course, we check to see how far it can bend before it breaks. But before the Fiberspar label goes on, every mast must pass the quality assurance test. First, load cells measure the weight and center of gravity. Next, the mast is checked for proper curve and stiffness. Finally, each mast is subjected to a strength test to ensure structural integrity. When the green lights come on, you can be assured that the mast has met all of Fiberspar's strict specifications. Mast curve and stiffness determine both performance and power. Without the right mast, your sail won't perform to its potential. To ensure optimum performance, FiberSpar engineers work closely with leading sailmakers to maintain their comprehensive mast-sail compatibility guide.
There's no mystery to matching mast to sails anymore. FiberSpar has a chart that tells everybody how to match their sail to their mast.
No matter what level of sailor you are, the advantages of FiberSpar's lightweight masts are obvious as soon as you try them. Superior reflex response means greater acceleration and overall speed. The narrow diameter means better aerodynamics and easier handling. State-of-the-art engineering results in a lightweight mast that is built to last. And most importantly, quality is guaranteed. Every mast we make passes the quality assurance test. Go faster with more control. Sail longer with less effort. Once you experience the FiberSpar difference, you'll wonder how you ever sailed without it.
Okay. Now, I thought the reason that would be interesting to show is really something really unusual happened while I was here at MIT. In fact, in launching this venture, I became not a sailor. In other words, windsurfing was so different from the sailing experience that I had. What it really became was really a business opportunity and also a personal challenge in terms of to try and start with an application where these materials were really not well accepted. What was revealing about those bending tests is that carbon fiber has typically been assumed to be a very brittle material. It can be very stiff and very light, but typically you can't fabricate structures which can be subjected to such extreme bending loads. And to really try and commercialize, based on this very narrow product, a company that was based on innovation in manufacturing. So we're located an hour southeast of Boston. I'm happy to say since 1989, when we really began production in earnest of windsurfer mast, our employment, we now have 65 full-time employees. We've been literally running about between 2 shifts a day and 3 shifts a day, 6 days a week since 1989. We supplied all of the masts to the Olympic competitors in 1992. Every single competitor used masts made by FiberSpar. And the real innovation, from my perspective, is not just in the development of the business based on what you perceive as a very narrow niche, but also the opportunities we have to expand based on the innovation in manufacturing. So what I have is just to illustrate a couple of points where I think that this is going and where we as an organization are trying to position ourselves to capitalize. And here's a couple of things. I've selected one particular industry because I think people in this room, many of us here, have some affinity or some affiliation with the Ocean Engineering Department here at MIT, which is celebrating, as all of us know, its 100th anniversary. And one of the things that I've selected just for an illustration is, one was a symposium hosted in Washington, the National Academy of Sciences, which was looking, there's nothing really magical about this except just to really illustrate that these materials are moving and have the potential to move beyond these very high-end sporting goods or aerospace applications. This conference was called in 1991, and coincidentally it was at the point where the aerospace companies were desperate to try and find new applications for composite materials. So this conference was, I would say, 95% attended by aerospace engineers and executives trying to get together with people in the marine industry to see if there may be some potential. But this was looking at, because of the lightweight and high strength, corrosion-resistant properties that a composite may offer, some potential applications in the marine environment. And here's another example where, for offshore structures, again, a symposium hosted at MIT, this one much smaller, but attending, I would say there were probably 75 attendees of all the major oil companies in the world. Each of them probably had 2 or 3 of their senior R&D people attending this, if you will, a very exploratory discussion, more or less, on what potential applications for advanced composite materials might there be in the offshore industry, where corrosion, exposure to marine environment or really caustic chemicals, in many cases a desire to reduce weight if the structure is being supported by hydrostatic forces, et cetera. So I guess what I'd like to just share with you today is really from the experience as a student at MIT and initially as a sailor and an athlete, the discipline and I think the focus that I had as a student and the focus of energy in sailing led to that initial identification of the opportunity, which was the windsurfer mast, even though I didn't windsurf myself. And I think what we see as an organization is the potential to cross over. We really are based in manufacturing, and our innovation, we feel, is in being able to produce high volumes of product at low cost, and they're sophisticated. But to begin, as our company continues to grow, to diversify into markets that have potential to be of broader utility, let's say, than the manufacturer windsurfer mast. So I'd like to just thank the opportunity here that I've had to share with you my own experience. Great.
Your masts actually have some glass in them, right?
Yeah.
What's the purpose of the glass?
Well, actually, there are two different types of glass in the mast. And what a composite is it's really, if people have heard of this expression of an engineered material, you can tailor the properties of the structure based on what its requirements are. So, for example, a windsurfer mast, it has a requirement to be extremely strong in bending, but then also where the sailor is attached to the mast, there's extreme point loading. He holds on just by that boom, and you can imagine the forces when the person lands in the water. Fortunately, I keep myself in the water anytime I windsurf. I don't try and go out of the water. So there's an example where radial loads and also external impact was a real factor. So we added glass to improve the toughness of the laminate by basically just adding wall thickness, essentially. So really, it's in many ways, the analogy is not too dissimilar to cooking in that you have, in a composite material, a lot of different ingredients. There may be Kevlar fiber, different varieties of carbon fiber, different types of glass fiber, and a whole host of polymer matrices that you combine in different ways to achieve some desired properties. So that's why there's a kind of a mix.
I was very impressed with your testing apparatus, and I did a lot of that at Boeing to test composites. I tried very hard to get a composite wing on the 777, but when that wasn't going to happen, then I left Boeing and helped Bill win the America's Cup. And when I talked to my buddies at Boeing, they say, well, don't come back until you can bring the cost down to something we can afford. Okay. So my question to you is, when are you going to bring the cost of a mast, a sailboard mast, which happens to be the same weight as my kite ski spar?
Yeah.
When are you going to bring the cost down below $100, and how are you going to do that?
Well, that mast actually we sell to our OEM customer for average probably $75.
Well, that's good. That's
Yeah,
good progress.
and one of the things about, it's a misconception about composite materials, that people think they're expensive because the materials are expensive. But oftentimes what you see is the manufacturing cost is so prohibitive that that's actually a larger driver, because just imagine if aluminum was a novel material or plastic was novel, people didn't have extrusion machines or they didn't have the kinds of apparatus necessary to produce things that were useful. So I feel, and one of the things that's motivating, you can ask in 1986, why get into a manufacturing company in Massachusetts? I think the innovation and the potential for innovation in manufacturing can really lead to cost reductions.
Well, if you can build a 3-pound mast like you showed in the picture there for $75, you got yourself an order for a large.
Well, the problem is if a windsurfer mast breaks, the guy falls in the water. If an airplane breaks, that's a serious problem.
They might still fall in the water.
Right.
Talking about kite ski, but let's talk.
Great.
All right, out here.
Peter, are there any in the windsurfing community now? Are there any sort of like vinyl LP proponents out there that like the old style masts for any sort of archaic reason?
It's pretty like aluminum when we started was a dominant material, and the analogy to tennis is very similar. You can't buy a wooden tennis racket now, even for the cheapest price. Same is happening with composites. The prices are going lower and lower. But maybe, Kim, should I pass on here or take another question?
I'll take one more. The gentleman out here, then.
Can you quickly comment on skis, snow skis?
Well, sporting goods is so rich for application of these materials in almost every sporting goods industry, whether it's bicycles or skis. Composite technology is being applied. There's a new development in ski design where instead of making the ski as a box, where you have a structural material like wood as a core. They're going to very lightweight skins that have essentially cores that have no internal strength, and they cap the ski. So there's this notion of a cap ski. And I think the same is true in archery, the same is true in fishing and fly fishing. I mean, in sporting goods, because people, like I say, are really willing to pay the price for the advances. And the prices of the composites are what's going to keep the materials out of more diverse and broader applications. But maybe one thing I'd like to say, there are really two of my mentors here that are also on the panel. And Jerry was an undergraduate advisor of mine in the ocean engineering department, and T.Van Deusen, who founded a company, Composite Engineering, who I respect very much. Also, while I was a student, allowed me as an undergraduate, and after I left the institute, to really experiment within his own facility while Ted was developing technologies for the manufacturing of rowing shells. So I just want to say really thanks to both of you, and it's partly a reflection on them that this activity has gone forward.
Thank you, Peter. And we'll move on to Ted Van Deusen. Ted, do you need the movable mic? No.
It's a pleasure to be before all of you and tell you about what I've been doing since I left the Institute. And I have a series of slides to describe it. Let's see if I can find the... Jerry, I know you kicked a lot of things on the floor. Oh, yes, here we go. Let's try it. I don't think I'll have as dramatic a talk as the other two, but I'll see what I can do. Let's see. Oops. Come from a background at Webb Institute and then MIT, and along the way I'd had an opportunity to get some work experience both at a large shipyard and a small design concern, and I wanted to be involved in a company that was doing design and development, but I also wanted to have the stability of manufacturing and be able to really get down to make things happen rather than just do designs on paper and hope that someone else figured out what you wanted and did it to what standards I had. And it seemed like I'd been a competitive athlete and a naval architect, and I developed a shell that seemed to be winning on a local basis. And it seemed to me sports equipment was a nice way to get a company started, because if you had something slightly better, it had an immediate market and something that you could start producing a limited number of, getting enough money to grow into a larger company. So I started building rowing shells, and this is kind of another view of one of our earlier boats. We were one of the first people to design a boat using composite materials because we wanted to make a lighter, stiffer boat. And we pretty much copied a lot of the wood construction, and there was a outer skin and then a truss framework inside to carry the load. And one of the problems we had was just trying to make room for the athlete in the middle of the boat, where we would have to get the athlete's feet fairly low, and just where the loads are highest in the boat, you have to cut a big hole for the athlete. So we tended to carry the loads through stringers in the boat, and you can kind of see a little bit what it looks like there. We ended up being very fortunate in 1976, the year I really got the company started, in that women were allowed to compete in rowing for the first time, and in the Olympics, and the U.S. women were considered to be very far behind the Iron Curtain countries, but our best single sculler, Joan Lynn, managed to come off with a silver medal in a very spectacular finish. And in winning the trials to represent this country, I think there have only been 3 races that our boats haven't won continuously since 1976 in choosing the best single sculler for both men and women. And it was just a fortunate thing that this happened just as we were getting going. And in the early 80s, the U.S. Olympic Committee did a study of how the U.S. fared in the world in different sports. And they discovered that the sports requiring very little equipment, which they termed low technology sports, would be like running, swimming, things like that, we did very well in. And sports like skiing, cycling, rowing that required a lot of technique and equipment, the U.S. fared worse than expected. And they set aside some R&D money to try to change that situation, because it seemed like the U.S. with all its technology should be doing better than anybody else in the world. I put some proposals in and got some grant money to do some tank testing, and my previous designs of rowing shells was based on trying to estimate and extrapolate from what literature was available of tests of boats. And this is my first opportunity to get into the towing tank and do some testing. And we took a parametric study of 4 different kayak hull variations and tested another 4 existing racing boats. And one of our tank models tested with 1.5% less drag than the best racing boats out there. And we very quickly took a mold off it and made a few kayaks. And the first 2 we delivered competed in the Pan American Games in 1987 and won 2 gold medals. And then a month later went to the World Championships, and the U.S. won the first 2 gold medals it ever won in kayaking in the history of the sport. And this is a photo of the fellow finishing. Greg Barton happened to be one of the developing paddlers who'd been working very hard and was just reaching his top performance level. We'd hired a top European coach for kayaking, and he was upgrading our whole level of competition. And then with the new boat, we'd like to think that was part of the whole formula for winning. And what's unusual about this, his style is that he's got such a lead, you can't see any of the other boats in the frame. He won by the 2nd largest winning margin in the history of the sport, and he's just coasting across the line. Based on this success, we were asked to do a complete fleet of kayaks, K1, K2, K4, and canoes for the 1988 Olympics. And this Greg Barton, and then he won a gold medal again, which was the first gold he'd ever won an Olympic competition. And then an hour later teamed up with another fellow and won a 1,000-meter K2 event. And this is the first time that dual wins within an hour had ever been pulled off, and was our first 2 golds ever. So it was quite a nice feat to have accomplished. I've just got a couple shots here. This shows a canoe. They're kind of unusual craft built to Olympic specifications. The main difference I would notice between a kayak and a canoe is a canoe has to have a single-bladed paddle and a kayak has a double-bladed paddle. Wanted to say a little bit about the competition theory. Many of the sports are being pressed very hard because the Olympics are getting so crowded, and sports like kayaking and rowing only have about half the countries that are entered in the Olympics participating in these sports, and they're trying very hard to keep the costs low and the equipment fair between all the athletes. And it seems to me that what we're trying to do is to find the best athlete, and equipment can lose a race, and there should be fairly small differences between equipment so that it's not going to make a winner for someone. So if you did come through with a breakthrough, that would probably create an unfair advantage and get controlled by the race regulatory bodies. But at the same time, we've seen the sport evolve from fairly wide, heavy boats a century or 2 centuries ago into very sleek boats that are very hard to handle. And every athlete has his own abilities in terms of conditioning and strength. And what we need is equipment that suits the individual athlete to be able to, for them to perform at their best. And what we've tried to do is make things as adjustable as possible, but just the fact that we have one particular model doesn't mean that that's the answer for everyone. And there's been some move to try to make one design boats to lower costs, but in effect, by choosing the design of the boat, you're choosing the athlete, and we've tried quite hard to keep that open. In going ahead and trying to improve the boats, I broke up my design effort into 2 areas. One was to improve handling, trying to make it more natural and easy to use. The more the athlete can relax, the better they can perform. By the time you get to the top international level, just about every athlete is in top condition, and very often the difference between winning and losing is how relaxed you are in the boat. Improve safety. these boats are pretty safe, but every once in a while you hear of an accident where someone's caught out in a storm and something happens, and just improved safety allows you to train longer in the year. And then we're trying to figure out ways of increasing the athlete's useful work, and that would kind of go along with relaxing, like I said, having the various adjustments and equipment be the one that would match the athlete's ability to put power out, and the water through the oars or paddles be able to accept that energy. The other side of design is trying to reduce the drag and other losses in the system, and that's really much easier to approach. Really, what we're trying to do is combine an art of figuring out what the human interface is and combining that with the technology of reducing the drag and increasing performance. Wanted to start a little bit on talking about handling. This is the women's two-person kayak K2 that qualified for the 1988 Olympics. You can see that the center of gravity is quite high and the boat's quite narrow. With the new kayaking stroke, the paddles extend a fair distance out to the side of the boat. And one of the unusual things is all of the boats I'm talking about here are completely unstable. You put them in the water before you get in and they want to roll over. You get in with a high center of gravity, and it's almost ridiculous. If you aren't skilled at it, you'd never really be able to keep them up. In fact, any designer who had never seen this evolution would be considered crazy to design a boat that couldn't be paddled. The interesting thing is the first kayak I showed you, I designed, and I said, well, you know, I've been rowing for 20 years. I'm used to a long, skinny boat. I better try this out before I deliver it. So I went down to the local beach with my friend who I'd done a lot of regular canoeing with. We got in the boat. I kind of rested the paddle in the water, tried to get my balance. I couldn't even pick the paddle up to take a stroke before I went over. We tried for about half an hour and decided it was completely unpaddleable, but I had to take the boat down and deliver it anyway. Greg Barton got in and pushed off the dock and said, oh, this feels fine. So I spent the next 2 years swimming and eventually learning how to stay up. I wanted to show this slide for stability. This is to scale. You can see that the cross-section of the boat in the water is extremely small. The athlete sits just about with the seat at water height. On the right, I have a rigid rotation of the athlete turning with the boat. And this is very much what happens when a novice gets in a boat. They're rigid, they don't relax, and for a certain amount of angular rolling, the center of gravity moves quite a bit to the side of the center of buoyancy. Those of you that are familiar with stability realize that you can pick a point. I've labeled M here as the metacenter, and if the center of gravity is below the metacenter, the boat is stable, and generally most ships are designed with several feet of metacentric height. Here we've got, well, there's an analogy too that the restoring force to bring the boat back to upright is proportional to the righting moment or restoring moment on a pendulum. And I've drawn on the side here pendulums, and you can see on the right the pendulum is quite high and upside down. It's quite an art to keep these boats upright. On the left, I've got a sketch where the athlete is very relaxed and is balancing himself to sit vertically, and the boat rolls, and you can see that his center of gravity deflects very much less. So the art in doing the design here is trying to understand what the athlete is going through in using the equipment, trying to push the design as far as you can to reduce the drag, but still make it paddleable or rollable. And one of the things is that when people go to organize a race and everybody gets there for a major Olympics, it has to be life-threatening conditions for them to want to call off a race. And you find that you have to race in almost every kind of condition out there. And maybe there aren't huge waves, but there's a lot of wind. There are various wakes and other things. And you pretty much have to have a boat that does everything well that it's going to see. In trying to reduce the drag on boats, we tried to figure out several different areas where we'd find a reduction in drag. We had a fairly limited budget, so we would be stuck only trying to test half a dozen different models and 2 or 3 different boats as controls. This shows us testing full size. As J.Milgram pointed out, the scale effects are really quite difficult to compensate for, and we're dealing with boats that have evolved for several centuries, and the difference between the best and the worst boat at an Olympic competition is probably about 4% in drag, and most of them much less than that. In trying to assess the effect of a change, you're really trying to read 0.1% difference in the tank tests. You don't have the budget to do it statistically to figure out just what's going on. It took the most difficult protocol in terms of setting up and measuring everything. The boats are so long and skinny, they deflect a little bit in the water, so we'd have to measure just exactly how they're sitting in the water and try to figure out what we could. And I'm plotting here the results of drag tests. This is a single shell. It operates in race pace somewhere between 4 and 5 meters per second, varying during each stroke. And starting at the top line, the top curve shows the resistance of moving through still air for the athlete, the boat, and the oars. And the next section below that is the wave drag. And you can see it's quite small, and this is because the boats are extremely long and slender. And the bulk of the drag is viscous drag or frictional drag. And everybody says, well, why don't you make the boat smaller and cut down the wetted surface? And what happens is as soon as you make the boat smaller, it becomes less slender, and the wave drag increases much more dramatically than you save in cutting down the wetted surface area. Shells are actually built slightly longer than they should be for minimum drag at steady speed, and that's because the athlete's sliding back and forth in the boat and depressing the bow and the stern alternately, and you can pick up some added drag from doing that. It's been a very hard thing to figure out just how to test that accurately, and we haven't done unsteady tests, although there have been a few estimates that it's in the order of about 4% of the total drag. We've tried to take that into account in the design, but it ends up suggesting that your boat be 2 or 3 feet longer than what it would be if you were testing steady state. For comparison, this is the drag off a K1. Again, it races slightly shorter distance, but just about steady 4.5 meters per second. And the top curve, again, is aerodynamic drag, somewhat less. It doesn't have oars, and you're sitting a little lower. The viscous drag is considerably less, and the wave drag is considerably more. This is because the boats are required to meet certain length and width rules. The K1 is 5.2 meters, or roughly 17 feet. And this is about 2 or 3 feet too short for ideal performance. Although if you could make a boat a little longer like that, you'd have to sit higher because you could no longer fit the seat as low, and it's not sure whether it'd be a faster boat or not. What's interesting is the two boats have almost identical total drags, and they both go just about the same speed. Just wanted to make some notes on structural design. We want to make the boat as rigid and as light as possible. They're very highly stressed in terms of fatigue, so you have to be careful in the design for that. And you'd like to keep as low a center of gravity as possible to aid in stability. The first shell I built, I designed to have about 1% less drag than the boat I'd been rowing. I rowed it extensively and couldn't find that it was any faster at all. And then I went back to the MIT library and started looking at what happens when you have a more flexible boat, and determined that I could account for most of the lack of improvement due to the vibrations in the hull, because I designed a more flexible hull even though it was lighter, and I was tripping the boundary layer laminar flow to turbulent much earlier, and it gained about the % drag that I had thought I was saving. And ever since the beginning, our company has tried to make extremely stiff boats. Other observations I wanted to make here is that just the flexibility in the footboard, the seat, and the riggers, anything that the athlete has to work with, seems to absorb energy. It delays the time that you can actually start to apply power. It's a very dynamic thing to be able to get the stroke with the oar or paddle in the water and get full force, and then get it out at stroke rates. And rowing in the 30 to 35 strokes a minute, in kayaking during a sprint they'll get up into over 100 strokes a minute. So you want everything associated with the athlete that they're pushing off to be as rigid as possible. You need the hull as a beam to be rigid. but you need to have some flexibility in the system. An athlete is not going to put the oar or paddle in the water at exactly the speed the water's moving all the time. And if there isn't a little bit of flexibility in the oar or paddle to absorb that mismatch, you get wear and tear injuries on your joints. So it's a thing that has to be quite carefully tuned to the athlete. This just shows a sketch of the loading on a single shell. You've got the crew weight in the middle, fairly minimal hull weight dispersed over the boat, and then the water weight supporting it. And this is just a scale to show you how slender the boat is, and it's really quite a challenge that required us to get into composites. We built our first boats using Kevlar and boron with some wood. The price of boron was about $250 a pound, and carbon fiber was about $400 a pound when we built our first shells. Since then, carbon has come down to be in the $13 a pound range, and boron stayed at 200 plus, so now we're doing a lot in carbon fiber. This just shows a layup of one of our single shell hulls in the shop. We start with a mold that's covered with a gel coat, and then we lay fabric and Nomex honeycomb in the boat. We basically have to be quite careful to get it all in right. We've got different layers going in every direction imaginable to try to get the strength the way we want. And when it's all done, we throw a sheet of plastic over it and seal it to the mold, and then draw a vacuum in the space, and that uses atmospheric pressure to compact the laminate and draw any air that's trapped between the plies out. And then we put it into a pressure vessel called an autoclave, and bring it up to several atmospheres pressure and bring it up to 250 degrees Fahrenheit, at which point the resin flows and cures. And this is the structure in our one of our early shells. There's stringers along each side forming the gunnels and the keel. Those are braided back in about 1975. We realized that we wanted to make longitudinal stringers with carbon and tried to find a nice way to do it. No one was really weaving carbon at any attractive price at that time, and I bought some old textile braiders and adapted them to work with composites and made the structure of the boat inside. Also, there's yellow tubes, which are actually arrows from a bow and arrow company, very light tubing. And then at the end, I had to make a lug to adapt it, and all of those are little braided end lugs that all have molds at every few degrees difference angle down the boat. They had to be a different mold. It was quite time consuming to put a structure together like this, but it avoided a lot of stress concentrations. And many rowing shells, either in wood or other composite materials, have the reputation of, after 5 years or so of hard use, of starting to soften up and get more limber, and they would then be relegated to training purposes. And it seemed to me that once an athlete bought a boat, they should be able to compete for a long time in that boat. It takes quite a while to adjust a boat and adapt it to yourself, and we tried to design any stress concentrations and fatigue out of the system, and we've taken boats back now about 20 years old and measured their stiffness compared to measurements we made early on, and they've seemed to hold their stiffness very well. So it was a good thing for us in that the resale value of our boats have stayed very high, and they've been quite desirable. This is a picture of one of the newest boats. We just came out with a new design in time for the last Olympics, and we were moving away from that internal structure with all of the framework just because of the time-consuming nature, but we ended up with a much more sculptured aerodynamic boat. Our previous boat was more like a wooden boat in construction, and this has no sharp corners, and it's made with unidirectional carbon fiber tape that's placed so it can kind of go around the cockpit and avoid the stress concentrations. We also were quite concerned about aerodynamic drag, and you can see the outriggers supporting the oars are a kind of an airfoil shape instead of the multiple round tube that's normally there. And we were expecting to save a little less than 1% in the total resistance. And as an undergraduate project, some students put one of our riggers in a wind tunnel and found about an 0.8% drag reduction. So we're quite pleased by that. And a few of the other manufacturers have talked about, oh, well, we tried that and it didn't work. Well, I think most athletes have trouble noticing in terms of just the feel of a boat when there's a change in drag less than 1%. And I think the whole goal of this adventure is to try to add up several small changes until you really have something. And this was just one of the details. This just is the finish of the last Olympics in Barcelona. The boat at the top is being rowed by Anne Marden. She's won a silver at the previous Olympics and was running in second to third place for most of the race and is just losing to the Canadian in the wooden boat in the final sprint, and she ended up fourth. It's the first Olympics the U.S. has competed in since '76 that we haven't gotten a medal in women's single sculling, even though the boat was by far better than anything we've done before, but that's just how it goes sometimes. This shows an 8-oared shell that we built using the airfoil riggers. Some of these are just so you can get a feel for what the different boats look like, although many of you probably have spent a lot of time in it. This shows a training camp in Florida. Going into this past Olympics, there was a feeling we might be able to improve on the drag of that single kayak that we designed back in 1988, and we had the chance to go back in and do some more tank testing, varying some other parameters, tested 4 more hulls, and ended up with a 1 3/4% drag reduction on top of the other boat. So we went into the Olympics with very high hopes. Greg Barton's in the foreground here paddling it. Handled slightly differently, but nothing that anybody couldn't adapt to. He ended up not being able to repeat his victory. He ended up taking a bronze medal, but it still was quite good. Here's Greg teamed up with his partner that they silver medaled in the previous Olympics in Barcelona, and again they just missed the medals. One of the things I noticed in competition at this last Olympics was that there were very few totally outstanding athletes that were head and shoulders above everybody else. In previous Olympics, you'd often see someone that was clearly better. Now it seemed like there were half a dozen people that could be on the podium getting a gold medal, and it was really all kinds of little subtle factors as to whether they won that particular day, and the competition was extremely close. We had about 45 of our boats being represented in the Olympics, and from starting first building kayaks in 1987, it's really shows how quickly you can kind of sweep into top international circles if you have a better boat. This shows the U.S. women in a K4. It's quite a fast boat. And another shot of a canoe. Along with the boat development, we worked on paddles. And going into the '88 Olympics, a couple of years ahead of time, Swedish aerodynamicists noticed the top Swedish paddlers were paddling with what they considered was a defect in style, where the paddle was going out from the side of the boat as opposed to coming straight back. And previous to that, to his work, paddles were basically drag devices. And he invented this paddle called a wing paddle, which is really a thin airfoil. And in the couple years preceding the '88 Olympics, all the top athletes changed to it, and no one made the finals in '88 without having one of these paddles. And it's been an evolution since then. We've tried 8 or 9 different designs, and as the paddle is moving backward and moving in someone's hand, it's very much like a propeller advancing sideways away from the boat. And it needs to be twisted, which this original paddle wasn't. And we did quite a bit of tank testing and video analysis of the paddle stroke. Here we just show several different designs that we had tufted, and we would have a paddler go down a towing tank with an underwater window and take videos of what was going on and trying to optimize the flow. What happens, though, is you find you need about 30 or 40 degrees twist in the paddle to get the optimum lift at the sections all the way up and down the paddle in the middle of the stroke. But the flow changes from almost coming in at the end of the paddle to going crosswise and then a little bit down the paddle. So it changes through about 130 degrees through the stroke. So it's such a compromise in flow direction that the trick is to try to get the paddle to work well at all different parts of the stroke. And there have been some major improvements in that area in terms of the way the paddle feels, and times have dropped. A typical time for a 500-meter sprint would be about 100 seconds, and the times have dropped about 4 seconds due to the change in the paddle. So this is one of kind of the major revolutions in sports, kind of like a fiberglass pole vault or something else. It's really had quite significant effect. I've also been quite involved in sailing. This is one of my loves, an international sailing canoe. We built our first carbon fiber mast in 1978 for a 505, and then got involved in the small dinghy classes that allowed carbon, which is predominantly now international 14s and international canoes. And for the small dinghies, the reduction in weight, of course, paid off in just less displacement and less drag, but really affected the dynamics of the boat performing in waves. They just have a much better motion. Because the boats are sailed upright, only at maneuvers when you're likely to make a mistake and capsize does the weight really affect anything to do with stability. But I was just at our national championships in the international canoe, and there was not a single boat there that didn't have a carbon fiber mast. The nice thing was the only one we didn't build broke, but we had quite a storm come through. It was about a 35-knot breeze, so it was kind of tough on these little boats. Recently, we've been trying to get involved in larger boat masts, but I just have a photo here of a close-up of the braiding technology we use to make those spars. And we've got longitudinal carbons, hoop wrap of carbon showing vertically on this slide frame, and then you can see little glass yarns going at plus or minus roughly 45 degrees. And we find the addition of a little bit of S-glass in the carbon greatly toughens up the mast. We have about 10% S-glass in the total. And as with sailboards, but probably less so, these masts tend to get quite a bit of abuse. And if you start a little crack, or if you have holes around a fitting, it's very nice to have a tougher material in there to prevent a crack from spreading. And the ultimate elongation of carbon fiber is 1.5% to 2% to failure, and the S-glass is around 7%. So the two materials work very well together. This is the largest mast we've built to date. It's a 92-foot spar for a single-handed around the world racer. And it just shows another shot of it underway. We've used the same braiding technology, just with a larger braider. One of the things that is really nice about braiding is that it will form the fibers around any kind of mandrel you put in there, and it's very easy to make shapes that are tapered in section and also tapered in wall thickness. And one of the harder things to accomplish in production kind of manufacturing is to be able to do tapered wall thicknesses. And this lets someone go in there and say, okay, I have this particular load, I want this much fiber in this direction, and actually weave it the way you want with long continuous yarns with no laps or bonds to worry about. It's really quite a powerful technology. And Peter told you about how he was able to specialize his company from making many small parts and getting a very attractive price. We've tried to aim toward going to larger custom parts, so we're doing very much of the same thing. From time to time, we get opportunity to work on unusual boats. This is an Australian 18-foot skiff. We did this 8 or 9 years ago. It did very well in the World Championships and is on display in the Sydney Nautical Museum. It's a kind of an exercise in carbon fiber and honeycomb. They're quite unusual boats. And then a designer had us build an unusual hydrofoil sailboat. Again, another exercise in carbon fiber. I was quite skeptical of this thing ever flying. Looks like our focus is a little tough. But it actually got up and sailed quite well. The main problems were involved in not enough R&D going into the sail control, but it lifted off and sailed quite quickly. One other somewhat related technology that we've been involved in is wind power. It doesn't really follow in the marine area, other than the fact that most aerodynamic codes are written for making propulsive power out of propellers, and the design codes are really quite different when you want to take energy out of the wind. And the general naval architecture background that one gets at the Institute here really prepares one well to go from original principles into studying a new technology. And I've been involved in forming the largest wind power company in the world. I was one of 4 founders for that, called U.S. Wind Power. And they're generating enough power about equal to 2 nuclear power plants. So we're saving quite a bit of energy, either in terms of fossil fuel or nuclear waste, and hopefully not burning hydrocarbons will somehow help the ocean environment. This shows a test set of blades we made that the Department of Energy is testing different airfoils at Rocky Flats in Colorado. This is a little better shot of a braider. I didn't know Peter was going to show you one in motion, which is far better than a still shot, so that's why I included this. This shows one of our blades under construction. We've got 2 skins, one down and one opened up with a lot of instrumentation. We had a few hundred little pressure tubes in there to measure the pressure in the airfoil and strain gauges. And then there's a wet out braided tube in there that's got a bladder inside. And as soon as we close the pieces up, we're going to pressurize the bladder and cast the spar right into the skin. And the spar is the main load carrying member. The skin just kind of smooths the airflow. This is just a shot of one of the wind sites in California. They're really quite dramatic. If you haven't seen them, they're just hundreds of windmills over all the hills. And it was a natural wind site because this particular one is just east of San Francisco Golden Gate Bridge. They've got annual average wind speeds of about 23 miles an hour, so there's quite a bit of energy to capture. And there's a large aqueduct going to Southern California with pumped storage facility in the water. So if you generate electricity and someone doesn't need it right away, you can raise the water and then get the energy back out. And we've seen quite a large development there. This is my shop in Concord, Massachusetts, about 18 miles from here. I'd love to give anybody a tour if they're out that way, so just stop in. And that's all I have to say. Thank you.
Question or two, and then we'll get on to our last speaker. Right here, front.
Showing towards the end the paddle. My question is, the testing and the design seems to be in some ways like what Jerry was talking about is the early approach to sailboat design, which was more intuition and brute force perhaps in terms of measurement. How have you come in terms of mathematical modeling and theory as to what a paddle really ought to be shaped like and how it ought to be used?
Basically, what we'd do is we'd try to understand the paddle motion used by the top athletes and then represent the inflow angles throughout the paddle during different parts of the stroke, and then try to figure out, it's pretty obvious if the top part of the paddle is pushing forward through the water that it's acting as drag and slowing up the system. So you try to rotate the thing around, just do basic engineering. The thing is, after you do that, you go give the paddler the paddle, and if you've got, say, 40 degrees twist in the paddle, when he goes to put the paddle in the water, it spins in his hand and he can't even get it in the water to take a stroke. So very much of it has been saying, well, I know where I can get an improvement. Now I've got to make it usable. And most of our effort has been on the human adaptive side of things, much more so than what the America's Cup has. I'd like to be much further along in actually doing it computationally, but right now it's very much more, in the paddle design, very much more of, let's think of a design, let's go out and see if someone can use it, and then go faster in it, come back, do another design to correct for that. And it's very much an evolution based on the people. Yes?
On that paddle technology, suppose you want to train athletes to put the paddle in the right place and take it out. If you just trail a couple of strings or you show them lights on the water, a trainer paddler for Olympics would know that the paddle goes in at one place, comes out of place. Trail strings in the water, shine lights on it so they know where to put it in. There must be an optimum.
There probably is, although different paddlers have different techniques, but in terms of one optimum, you want to, since the paddle starts very close to the side of the boat and travels outward at about a 45-degree angle with this new wing technology, and if you do a photograph or a series of videos with the reference frame of the water, you find that the paddle actually goes straight sideways away from the boat in the water. It doesn't really travel backwards at all. But what you want to do is have the boat as narrow as possible. One of the things I didn't mention is that we changed the shape of the boat to make the boat extremely narrow where you put the paddle in, and we've gotten several inches more paddle stroke with this new paddle. As for where the paddle comes out, it depends on just how the paddler likes to paddle, and there we have several different design paddlers. Some like to come back more and some like to go out to the side more and turn over at higher or lower cadences. And if you drag something that you'd actually look back and see where the paddle was coming out of the water, you'd have major stability problems. I think the best thing is to analyze videos, and I think from actually seeing people move, or the athletes watching themselves, they'll see where they look awkward or see where they look natural, and you can kind of work toward that. And the other thing that's been very helpful is just recently there have been some fairly accurate speedometers that you can time yourself over different distances with. And it seems like a fairly trivial thing, except you realize that all of these boats are surging quite a bit every stroke, and what they've had to do is work out the circuitry to average over a number of strokes and start that average period at exactly the same place in a stroke. And those have helped people evolve to new shapes very, it's been a big advantage.
Okay, we're going to have to move on here, and thank you very much. Next speaker is D.Liu of the American Bureau of Shipping.
Good afternoon. My life after MIT, when I graduated here, I went to work for one company, and that's the American Bureau of Shipping. And most of my life has been with big ships like oil tankers, container ships, and commercial ships. But nevertheless, I was asked to speak on tourist submersibles, and I think it's, I don't know. First of all, I'd like to ask the audience, has anybody ever been aboard a tourist submersible submarine? Okay, fine. That's more than I've been. I have not been aboard them, but we as American Bureau of Shipping, we class them. And I think it's perhaps just a change of venue that we've heard all about boats on the surface. We'll talk a little bit about boats beneath the surface. Basically, the evolution of the manned submersible industry is an incredible story. The purpose of submersibles when they first began was really to do research and observation. And since then, they've really gone into a commercial venue. And vehicles that were designed to carry 1, 2, or 3 people are now designed to be much bigger and to carry 40 to 50 people. And most of those people being civilians. The most remarkable aspect of the submersible business is that this evolution really occurred only during the last 30 years, and most of the commercial business has been developed over only the last 10 years. So there's money in that. But basically, the design and construction of submersibles must meet certain design and safety standards of a classification society, such as the American Bureau of Shipping, for which I work for. And I'll just mention a little bit about class. We establish and administer rules for design, construction, and the fabrication of marine structures, primarily big ships, but we also cover tourist submersibles. And as a matter of fact, we class most of the submersibles throughout the world. And classification certifies that a vehicle possesses the structural mechanical fitness to operate safely. There are currently about 30 tourist submersibles around the world. And Jacques Piccard is credited with designing the first tourist submersible, which went into service in 1964 at the Swiss exhibition at Lake Geneva. And it was in operation for about 15 months, and it carried about 32,000 tourists to the bottom of Lake Geneva, which is about 300 feet. And after this exciting start, then tourist submersible development languished for about 20 years. And then in 1985, a company in Canada at the time called Subaquatics was formed to design, build, and operate tourist submersibles. And if I can, I guess, have the first slide.
You got it. Whoops.
Oh, I guess I had it and I passed it. This is an Atlantis Submersible, and it was built by Atlantis Submarines, as it's called now, in Vancouver, Canada. And it's probably the first modern submersible built, again, in 1985. This company is one of the largest. It currently has 12 of them operating, and they operate in very nice areas where obviously the water is very clear. They operate in Hawaii, Grand Cayman Islands, Barbados, St. Thomas, Guam, Aruba, and Mexico. That's where this company operates. And if you look at this vessel, it looks very familiar. If you've been to Disneyland or Disney World, it looks very much like the submersibles there, or not submersibles, but the submarines. Here are some facts about the Atlantis Submersibles. The Series 1 is 50 foot overall, 13-foot beam, 8-foot draft. That was the first that they developed, and it carried 28 passengers. And the Series 2 and 3 were the later versions. They're a little bit bigger. They carried 46 passengers. And again, in both cases, they have a crew of 2. The Series 1 cost something like $2.5 million, and the Series 2 about 2.9, nearly $3 million. Weight, talking from 49 to 80 tons. Operating depth, Series 1 and 2, 150 feet. Series 3, 250 feet. Most of the submarines operate at about less than, probably about 150, 200 feet. As you go deeper, there's always scuba divers, and below a certain depth, scuba diving becomes a little bit more dangerous, so they try to keep it probably about 150, 175 feet. And again, it's classed by our company, ABS. It's also insured. Buoyancy, basically, there's sealed water tanks. There's ballast tanks in the vessel. One of the things about submersibles is safety. So far, there's 30 operating. There's been no loss of life, and believe me that most companies are very concerned about any accidents, because all you need is one accident on one submersible, and they're probably all out of business because of just the negative advertisement about that. But they do have, on submarines, they have a fixed ballast system, which is weights, and they can jettison the ballast in case a submarine underwater is in any danger. You can release the weight, and the submarine will always rise. So it's a very safe vehicle. Again, safety features, there's redundancy throughout the system, and there's also a surface vessel escort vessel that's above the submarine, and I'll have some pictures of that later. It's always in radio contact with the submarine below. And also there's navigation systems aboard. This is an Atlantis submarine out of the water, and it's constructed of a steel cylindrical hull. There's the steel hull, and then above it this is fiberglass, and then beneath it there's some skids for landing on the bottom. And then there's thrusters that you see fore and also aft. It's propelled by electrical thrusters and powered by large banks of batteries. This shows the interior view of the Atlantis sub, and the batteries are hidden underneath the seats. They're all under here. And this one here, I think, is a 48-passenger vessel. The battery box is equipped with hydrogen detectors to warn the pilot of any malfunction, and the batteries have to be recharged overnight for about up to 8 or 10 hours. So the submarines operate during the day, recharge during the night. Here's a bird's eye view of the pilot at his controls in the nose of the pressure hull, and it almost looks like an airplane cockpit. And also the guy that drives this thing is called a pilot, not a captain. This is a photo of another submersible, and this is not Atlantis submarines, but it's called the Sinbad, and this tourist submersible is a Mark III, and it's built by a company in Turku, Finland. Again, this is another very large manufacturer, and it's again designed to carry 46 passengers and a crew of 2, and maximum depth of this vessel is also 250 feet, and this particular one's operating in Egypt. And there's also sister vessels that are operating in France, in Mallorca, Spain, and in Taiwan. Here's another Mark III sub, and it's an Italian one, or it's operating in Italy. Visible in this photo are 3 tanks on the side of the sub. 1, 2, 3. And the middle tank holds the high pressure air supply, while the other 2 tanks are the ballast tanks. They take in the salt water. The ballast tanks are used to change the buoyancy of the sub to account for changes in the total weight of passengers from one dive to the next. Basically, once all the passengers are on board and the hatches are closed, the pilot will pump water into or out of the ballast tanks in order to get neutral buoyancy. And then they use the thrusters to move the vessel, take it beneath the surface, and also to bring it back up on the surface. Here's another Mark III type sub being launched called the Looking Glass. And basically on all these submarines, we require that there always be 2 hatches, 1 forward, 1 aft, particularly for those carrying more than 6 passengers. This particular sub has a displacement of 106 tons. There's another one. There's a 22 acrylic viewports on the sides of the sub, along here. And then of course there's one that's in the front so that the pilot can see, and also that the passengers can have a very good view. And the acrylic viewpoints are designed and fabricated according to an ASME standard. The viewports are a critical system. They're acrylic, and after a number of cycles, they do fatigue. So, and they also have to keep them very clean and prevent them from being scratched. Here's the newest, most revolutionary submersible. All the ones you've seen prior to this slide, are basically pressure steel. The pressure hull is made out of steel. And this one here is called the C-Bus, and it's manufactured, can you focus that? It's manufactured in France by a company called Comex. And basically here you see the steel rings. And there's a big, large steel part of the hull forward and also aft. And then there's these steel cylinders down here. Basically, the entire structure is acrylic. You don't see the acrylic yet, but this is the frame by which the acrylic will be around. And the idea, of course, and you're in the business of tourist submersibles, you want to have as much viewing area as possible. And this is quite revolutionary in this design that you can see. Well, here's the fiberglass deck. The acrylic you still don't see, but there's very large acrylic cylinders that would be put into this structure. And the battery pods the batteries will be put in these cylindrical pods. And the batteries are used also, they can be shifted, the weight can be shifted of the battery in order to trim the vessel. Very, I guess, very advanced technology here. In reviewing this design, here's where it's built, and you can see the acrylic cylinders. Again, the acrylic cylinders take pressure loadings, but it's very poor for taking bending loads, and all the bending loads are taken out by the steel frames, bending, torsion, and those sort of loads. So this is the newest technology in submersibles, and I'm sure if you're a passenger on that one, you get a very good view. This particular vessel carries 50 passengers and cost something like $3.5 million. And it was operated in the Mediterranean off the coast of Monte Carlo. Here's another submersible. This one here is designed by Jacques Piccard of Switzerland. And this shows the pressure hull, and it's called the SPT-16. It carries 16 passengers. And it's fabricated by Sulzer Brothers. And this photo shows, actually you can't see it, but there's strain gauges on the pressure hull. And the thing is suspended by its lifting lugs. And this is one of the design conditions of a submarine, is that generally they're lifted in and out of the water, and that does put quite a bit of stress on the hull. So that's one of the tests that is undergoing. This one here was small enough that, well, it's hard to see here, but you have the submarine hull here, and this is inside of a hyperbaric chamber. Our rules require that all submarines be tested 25% above its rated depth. So this one here was small enough to be able to put into a pressure chamber to test it. In most cases, the Atlantis submarines, the big ones you see, they actually take it, drop it down into the water unmanned, and drop it to a depth that's 25% greater than the operating depth. Make sure that it withstands that pressure. Basically, haven't you shown you what these turret submersibles look like and how they're built? I just want to give you just a brief overview of what a typical turret submersible operating scenario is like. First, a tourist buys a ticket, and by the way, a ticket, as I understand it, in Hawaii costs about $70. In other places, about $60. So on average, it costs $60 to $70 to take a ride in one of these. And then they go to a dock area where they board a ferry boat, a transport ferry boat. Oh, sorry, and they ride out to where the submersible is. And they go out to the dive site. Then the ferry boat rendezvous with the tourist sub, and it offloads the, let's say, 48 passengers, and also unloads the 48 that are due for the next dive. And I just showed this as one that's at least on the surface. And the most dangerous part in the operation of these submersibles is really at the point where they're doing the at-sea transfer of the passengers. That's the most dangerous point because you have two moving platforms. And anyway, from an operational point of view, that's considered the most dangerous part, not the part that you're underneath the water. And then what happens is with all the tourists on board, then generally they get an orientation talk about safety, tell people about emergency exits, life jackets, and breathing equipment. Then the dive is made, let's say down to about 150 feet, and it follows a standard flight plan, usually a scenic route along the bottom, and generally there will be some sunken small boats or ships or something that is very scenic for the people to look at. And generally maybe a diver will come down and feed some fish. One thing, this is the surface support boat. This is the Atlantic for the Atlantis Submarine. And the dive usually lasts about 45 to 55 minutes. And the surface boat actually goes above the submarine at all times because, again, when the submarine's below the water, you can have some other recreational boat, like a sailboat, come over it. And just maybe there's an emergency at the time, and the submarine has to surface. So there's always a boat like this that really just mimics the motion, the path of the submarine. Also keep boats away, yes. And also they're in continuous radio contact, and generally there might be a scuba diver aboard too in case there is an emergency. Basically during a day, the vessels make about 8 to 12 dives. Some even operate at nighttime because you can put lights down there. I guess Professor Edgerton's strobe lights, and also get night trips as well. At the end of the day, then a boat like this would tow the submarine back to its base where it's cleaned up and the batteries are recharged and so on. To date, there's been something like 1.5 million passengers that have taken tourist submersible rides, and I think a lot of these companies are hooked up with cruise ships, so that I think as the cruise ship business has been growing, so is this business, because I think everybody that comes to a port and you're on a cruise ship, and if you have an opportunity to ride a submarine like this, you probably would take it. So apparently it's a very, very good business. 30 submarines out there, and there's more being built. So hopefully, if you ever get a chance, I wish I could, take a ride in one. Thank you.
All right, thank you. A couple of questions for D.Liu.
About a knot or a little bit less than a knot. You want to go slow because you want to, the people have to see. Plus, the thrusters aren't that powerful anyway. So little less than a knot. Yes, sir.
Your tankage arrangements for variable weights, you have a set of main ballast tanks to bring them in and on through, and then
Yeah, usually they had the ballast tanks on the side. And what you want to do is get neutral buoyancy, and then they generally, I think, use the thrusters to go down, and the thrusters to come back up. So they will take on water basically I don't think they use it really for descending or ascending. They use the thrusters for it. Sir.
how do you maintain radio communication surface?
So I think it's a radio telephone, I believe.
Waves are able to get through the water without.
I believe so, yes.
Yeah.
I'm not sure, but
Acoustic telephone, perhaps?
yeah. Yes, sir.
What's your fail-safe criteria for the acrylic? Could it sustain a spear gun shot without fracturing catastrophically?
Gee, that's a good question. I really don't know.
What was the question?
There,
Question
Could-
was,
well, could the
Repeat the
acrylic
question,
withstand a spear gun shot in terms of the strength of the acrylic? I suppose it could, but there are.
I'm aware in the early days of commercial jets, we lost a couple of plane loads of passengers in the Comet because of inadequate damage tolerance and criteria. It was a regulatory problem. And I'm just wondering if maybe the submarine industry is not susceptible to that same type of catastrophe.
Yeah, I thought the Comet was because there's too many square corners in the openings that they had a high stress concentration.
A little crack had to be a big crack
Yeah.
instantly.
But the ASME, there's a pressure vessel human occupancy standard for acrylics, and that's what you have to meet. But there is this, I think it's, most acrylics are good for something like 15,000 cycles of pressure loading. So there is a life limit on these acrylics. So that is certainly a consideration. And also, you don't want to get a lot of scratches on the acrylics either. A lot of stress concentrations there. Yes?
You may have covered this, but what is the operating pressure? Is it 1 atmosphere inside the sub?
Inside the sub, it's just normal, yeah. And there's also air conditioned. It's just, you just walk in and it's just ambient pressure. Yes, sir.
Is there any equivalent to the gentleman from the aerospace industry who went to aircraft is subject to A, B, C, and D checks? And I wonder, is there anything like that imposed on the operators of these vehicles? After so many thousand cycles, you have to go in and rip out the acrylic and replace it.
Yeah, there is. There is, again, they have to record the number of dives and in order to meet our rules, because they do have to be inspected on a yearly basis too. You have to be taken out of the water, obviously, and to go through a thorough inspection.
okay, I would like to spend the last few minutes giving people a chance to ask any further questions of any of the speakers in the panel. So at this point,
Peter, you might comment for the audience your contribution to the America's Cup race.
I guess our contribution, I had a question. Well, we produced, the sails are made of a material which is relatively stretchy compared to a rigid material like a composite. So we produced full-length tubular battens, and those of you that watched the America's Cup, we were pleased in that we were able to reduce a significant amount of weight out of the battens, but also the Italians in the last race broke battens. And with all the investment in technology, such as Jerry and others, a broken batten can what does a broken batten, Jerry, do to the aerodynamic predictions of the sails?
Well, I expected it to be terrible, but I noticed that the Italians slowed down very little when theirs broke, so the answer is I don't know.
That's the wrong answer. The battens make a big difference.
Yeah, but I have to be honest.
But anyhow, we supplied Bill Koch's boat exclusively. We didn't work, although we had many of the other boats interested in our battens. They were much lighter and they were very durable. We supplied their team exclusively.
Peter, I noticed in your film you make quite a weaving that you were doing. Now, is a fair amount of your strength of the mass due to the weaving? In fact, I was thinking rather than where you weave that, but try to apply that
Yeah, the trick with a fibrous material is to try and have the flexibility in a manufacturing process to be able to change fiber orientations. And the advantage, as Ted indicated as well, with for small tubular structures, this traditional braiding technology produces a seamless form, and there's some flexibility to change fiber orientations, but by no means is it the only method in which you can achieve a similar end. So really part of the creativity comes in with adaptation of manufacturing technology and textile technology in particular to get fiber placement and varieties of fiber placements in a structure. So it's not the essential ingredient, but it's just a means of achieving a certain type of fiber placement and certain fiber orientations.
Let's see, I'll be a straight man for Ted. You might want to comment on your contribution to MIT's human-powered hydrofoil, the world's fastest.
Well, it was a fairly small contribution in that they were looking for some hulls that would keep them afloat and let them get up to speed when all the design really took off and flew. And instead of having to recreate a hull, we were able to let them use the kayak hull forms that we had to create just a light hull. So we were hoping we'd find a reduction in drag with the transom stern. Some of the destroyer model tests suggested that we might. And we tested a rowing shell first by taking one of our models that was just a little bit off optimum because we wanted to save the optimum model to make a mold from. And we reduced the water, we made it ahead with bulkheads in the stern and reduced the waterline length 5 and 10% of the length and towed it, and we got a drag reduction at race pace in the order of about 1%. And we built a few boats, and they seemed to fare about like any other ones, but they were a little bit more difficult to avoid bouncing around when you rode in, but basically worked reasonably well. And a few years later, we got back to go into the towing tank with one of the optimum models that we'd done, and found that we didn't get that drag reduction. What actually had happened was we had picked a model with a center buoyancy a little too far forward from optimum, and when we put the transom on, we had moved this center buoyancy close to optimum. And I guess the changes were so small, it's kind of hard to separate those things out. We tried to do the same thing with kayaks, and they're very clearly the wetted surface associated with the transom shape increased the drag immediately, and there was no doubt about it. It seems like possibly if you're getting up at food numbers of 1 or over, which is most of these shells and kayaks are operating at about 0.6 food number, you may start to get some benefit from the transom, but at the speeds they're going, you don't get much of a drag reduction in the waves, and you really increase surface area.
Can you accurately predict the change in materials and patterns that you use on the properties, on the functions of what you're building?
It's really quite accurate, in fact, that the actual mechanics involved, if you're in the aerospace industry, the answer is really no, but if you're working in other applications where resolution in terms of stiffness or mechanical properties or thermal properties, there's fairly good analytical methods based on mechanics, really, that allow you to predict properties quite well. Strength, on the other hand, is very difficult to predict. You can get sort of elastic properties and thermal properties, but strength is one of these issues which has really plagued the composite industry, and all of us that are sailors are familiar with many examples of whether it's a mast falling down or a windsurfer mast breaking or a rudder post in the Fastnet race failing. That technology is not really quite as well developed, and that's led to a lot of caution, I think, in terms of use of these in applications such as the aerospace, where lives depend on the performance of the structure. So physical properties, yes. Strength, no. And that's an area where there's a lot of academic work in a place like MIT and other institutions to try and get a better handle on the analysis of the failure modes.
Any comments on the demise of Coyote?
I don't know. Who knows about keels falling off? I think as far as my knowledge is limited. I don't know, Jerry, do you know more about that boat?
Well, I do, but I'm not in a position to talk about it.
Okay.
Someone else who hasn't asked a question?
In regard to future America's Cup races, and an idea to minimizing the wind variation, has there been any talk about fixing the site of future cup races?
Well, there's been lots of talk, but the problem is right now, by the deed of gift, the last victor has the site. The last victorious yacht club, not the individual, and there's been a lot of acrimony over that, because there are many people right now who feel that San Diego is one of the worst places to sail for the America's Cup. But the San Diego Yacht Club doesn't feel that way, and their choice at the moment is theirs. And I would hope that there would be some kind of an agreement soon, where the winner has the choice of venue. It will make it a much more interesting event.
Peter, I got the privilege this winter to have three young windsurfers who are sponsored, two of whom sponsored by your company, one of whom is sponsored by a company that makes masts out in Hood River area. And we were breaking, let's say, on the average of 3 masts a week. So we got to get a pretty good feeling as to what worked. We do know the fiber spar mast went a heck of a lot faster on the racing sails. But in terms of the extreme activity, something in the other spar was a little bit better. We really never got a handle on it. We understand you're looking into some of the techniques that the other people are using. What are they doing different? Because we never really figured it out.
Well, you must have had unusual unusual testing in that.
Well, we do break a lot of mass.
Yeah, but I think what you find is that because of the nature of the sport being as extreme as it is, that there are certain conditions that will break any product. And as an example, the masts that we manufacture are used by like 90% of the World Cup athletes. So what happens is if they're sailing in extreme conditions, you find often that the top athletes will have more failure with the product that they use most prevalently. But we don't think that there's anything inherently. I think there are certain things when for example, in that video, there are certain things that people can do as the sport has progressed that put such demands on the equipment and make it very difficult for the equipment to withstand it, no matter what the materials.
Well, most people don't do this stuff. I mean, let's be honest. It's only about 2 or 3% of the people that break 90% of the mass.
That's right.
Mostly it's a keep-up.
Right, that's true.
But I was just wondering if you knew anything about what some of the other people are doing technologically and how you're planning to answer it competitively, if indeed you thought you even needed to.
Well, I think you always need to present a moving target from a product standpoint, and I'm sure Ted can attest. When you put a product into the field, the mass that we've had in the market has essentially been the same for, let's say, 5 years. You need to always present a moving target, because what happens is people will be able to eventually approach your technology, at least if it's a market that has any merit at all. You'd hope that, it's a sign if people don't do what you're doing. There's some, I think there's maybe an indication the market is maybe smaller or more narrow than you might suspect. And I'm sure in Ted's case there were, for example, opportunities where people, after seeing a product, they can evaluate it and see technically what's making the product perform well, and then approach that. And the objective is to then take the next step. So it's sort of a continuous improvement is really the nature of manufacturing. If you don't improve, eventually someone's going to produce a better product. So I think that's a very general answer to your question, but if we feel there's a better product in the marketplace, we certainly, you can't just sit back. You have to respond in terms of making the technology move forward. So.
We're beginning to run over. I think we'll take a couple more questions, and then I'm sure our speakers will be willing to hang around for a few minutes to talk to any particularly ardent seekers. So a couple more questions?
A question for Jerry. How much of the velocity prediction program was developed exclusively for the A3 syndicate, and how much of it was just developments that you've been working on throughout your career?
Well, we've been developing those programs over years, and as I indicated in the talk, the key to getting accurate predictions is the models. The models, most of the models that we had before were upgraded for the America's Cup program, And the sail model developed with the Sailing Dynamometer was done exclusively for the America's Cup program.
One more?
I suppose if it was a larger market, we'd attempt to do that. Although I think in many ways it's a little disruptive for an athlete to change equipment. That balance and ability to perform at your maximum is so sensitive to any change you make in your equipment that you wouldn't want a boat that was dramatically different. And if it's at all possible to incorporate changes in the design so that you don't have to change equipment, that would be the preferred approach. I'm trying to think, the Pan Am Games in '87 I referred to, we saw a newspaper clipping saying that the boat had won a 1,000-meter race by 20.3 seconds. And we say, normally the winning margin is hundredths of a second, maybe a 0.2 of a second. How did it get to be 20? And it turned out there were extremely strong tailwinds and fairly large waves, and the other boats were bearing their bows, which are generally quite long and narrow so that you can get the paddle quite close to the center line, whereas most of the volume of the boat is aft. And from the boat designs I'd done in shells where I had to worry about the pitching of the boat, I then designed a little bit more volume above the water, so it didn't affect the flat water performance, but it did enhance the wave performance. And that boat, just won by such a huge margin because of the conditions. That's the type of thing. If you can do it without compromising, it's much better. But there are probably some conditions where you'd want to minimize your profile above the water to crosswinds or something like that that might be beneficial, particularly in the canoe, which is extremely hard to control. You're paddling on one side, and generally, if the wind's from one side, all the people that paddle on the off side do better. And it's kind of unfair that way. But there are some changes in a larger market. You'd go after that. This really is an extremely small market. There are probably just a couple hundred paddlers that are doing this type of sport in the country. Of course, rowing's quite a bit bigger, but still, in terms of manufacturing, it's not very large.
Well, thank you very much. We should give our panel a round of applause, and thank you for coming.